about me. The only main thing to remember is I'm not a geologist, so I'm probably going to say something stupid. So take it easy on me.
What's different from everybody else?
You may not have heard of Data 61 before. That's just a group within CSIRO. We're the digital research group. We work across all different domains, software systems, robotic systems, analytics, machine learning, cyber security. We have a large engineering, software engineering and user experience design team, working in all different domains. My work is predominantly with mineral resources, and I work closely with my colleagues from the Mineral Resources Group in CSIRO. This is an overview slide of kind of what the ideal situation is that we're trying to achieve with applying data-driven algorithms in this domain, which is to take all the data that we have, all the features that we can derive from that data, any existing models we might have, use machine learning to produce some ideally probabilistic output, and ultimately inform some decision from that. That's what we want. We want to be able to take the output and have it make an actual difference in the way we operate, and all the while incorporating our geological expertise across all domains within geoscience. So what I'm going to talk about is some examples of us applying machine learning algorithms to geoscience problems. So the six examples, and these are our partners. The first four are from some work we did with GSQ, then an example with GSSA, and I'll finish with one's a little bit different, drill core characterisation, some work we did with BHP. So all the first problems are located in this region in the Northwest Mineral Province in Queensland. And Matt Greenwood from GSQ is speaking after me, so he might give some more of the geological context to some of these problems, and I'll focus on the data analytics side of things. This is the area of interest, and this is the data sets that we're looking at. So geochemical surface, geochemical surveys, geophysics, remote sensing, satellite data, DEM and any derived products, and existing interpretations that GSQ have developed already. And the problem was to investigate how machine learning can help us understand that data and the region. So we spent some time with GSQ and identified a few different problems to look at as examples of where machine learning might help. The first one we chose was mineral occurrence mapping, because GSQ had already applied a certain data-driven approach to mineral prospectivity in that region. That's the weights of evidence model, which is relatively common and as Vlad pointed out, it's been around for a long time, along with machine learning approaches as well. So we just wanted to do a side-by-side comparison of the two for the exact same data set in the exact same region. I'm just pointing out there some of the differences between the two, and some advantages I think machine learning has over weights of evidence, in that it can handle different types of features, can handle features that are dependent or correlated, whereas weights of evidence needs to have conditionally independent features. I think that was your point earlier, Oscar, your question. And it has a robust process around model validation about separating out your data set, training and test sets to evaluate how well it's doing. This is just the example of the region that we looked at and the output of the machine learning model. I guess the thing to focus on is the comparison of the ML model with the weights of evidence model. So that's the ROC curve showing the true positive rate as false positives go. So the faster this curve grows, the better performing your model is on the data. So the weights of evidence model is the orange line there, and the cross-validated machine learning model, which is the more correct way to do it, is the green line there. The problem with this type of data-driven approach in this context is, as Vlad pointed out, the amount of data we have is very sparse. We have very few examples of existing deposits in this area. So from a data-driven perspective, applying a purely data-driven approach may not be the best method for producing a prospectivity map. We have very few positive targets. We have no explicit negative targets. We know roughly, there isn't a deposit there, but there's no exact locations where we know definitely that's not a deposit. The data set is extremely unbalanced. There's a few different problems with that, and Vlad gave some alternatives that I'd agree with his comments around that in terms of prospectivity mapping. Other ways to tackle that problem, probably a knowledge-based approach, such as fuzzy inference systems, or broaden or change the data-driven problem to train on, say, assay data from drill holes instead of deposits where you have very few examples. Ultimately, you produce a map like we did, but the problem comes down to how do you validate that model, and that's still kind of an open question. Ultimately, you have to drill a hole to validate a prospectivity model. The next problem we looked at was classification of outcropping granite. So for this model we used 9,000 surface observations from geologists on the ground, and the covariates, so these are the layers, the predictors or features, were remote sensing data, DEM, and derived products, and some geophysics as well. And we used a random forest classifier. So I'm showing here the results from, this is GSQ's interpreted geology model. So based on the same data sets and the same surface observations, but done manually. This is the model predicted output. So you can see it does, and this is, the difference here, so in blue areas, the two models agree, and the red areas are highlighting where they disagree. And the model probability is shown here, so higher. Yellow is higher confidence, the model has higher confidence in the output. You can see it does very well for the black regions, which are not granite. This particular pink type of granite performs quite well, not as well with some of these other types of granite. You can also see the model is less confident where it's also wrong, which is good in some sense. It's a highlight there of an area where there's disagreement, but also where the model is quite confident in its prediction. So that's something to look at. You've got essentially two models, a manual model and a data-driven model, based on the same data set, coming up with different answers. And regardless of which one's right, you'd like to know the reason behind that. So that requires some expert intervention to dig a bit deeper. Here I'm just showing the model's prediction outside the outcropping area. So could you use that model to predict regions that look like outcropping granite that are currently, we think, is undercover? So it highlights a few areas that are potentially outcropping granite where we think it's undercover. And again, that's something the geologist would have to look at and say, no, the model's wrong for this reason, or maybe that area is misclassified and it's worth another look. The next example we looked at was along the same lines of the geological classification, but can we, given the interpretive geology, audit that process and look at areas where the data disagrees with the geologist's interpretation. So here we're using an unsupervised machine learning algorithm called a one-class SVM, which is an anomaly detection algorithm. So the anomalies we're looking for here are not geological anomalies, but they're anomalies in the interpreted geology. So we have 30-odd classes of geology, and for each class we look at anomalies within the geophysics data. So geophysical data which is different from the majority of the data within that class. So what I'm showing here, the way this algorithm works is you have to kind of seed it with an expected amount of anomalous data points. So in an extreme case, I'm showing here what it would look like if 50% of the data was anomalous. The areas in purple there, 10%, and then say 5%. You can picture this as in a high-dimensional space, the algorithm enclosing all the data in a sphere or an ellipsoid, and it's a most compact way of encapsulating the data, and then highlighting the points that are outside that sphere that look a little bit different. So again, that's pointing out areas where geologists could take a look and say, these points in the data disagree with everything else we've classified as this type of geology. Is it correct? Why is it different? And focus on those areas to see if there's any potential errors in the interpretation. The next example is a geochemical modeling example. So here we are looking at, we want to predict the chemistry in this region undercover. So there's some assumptions going into this model that we have soil surface geochemistry readings from all these blue points, and we have geophysical covariates. Is there any information in the geophysics which relates to the surface geochemistry, and could that indicate the geochemistry undercover if we look at the geophysics in this region? These are our training samples. This is the area we're interested in predicting. We used, again, a random forest regressor. And in this case, we also used a classifier to try and understand where the model is valid. So this was mentioned earlier by Mark, I think, and maybe by one or two of the other speakers about some of the limitations of machine learning is understanding the area where the model is valid based on the distributions of your training data and the area you're trying to predict in. So we call this covariate shift. So I'm going to give an example just to explain it here. Let's say we have training data with, so this is just in 1D. We have covariate X and our training data distribution looks something like this, but we want to predict over an area which has a slightly different distribution. In one dimensions, a simple linear regressor model given this data set might do something like that. In cross-validation, if we split up this data set, it may perform very well to predict some target Y. We get a new area where we want to make predictions where we don't have the target Y. Represents this area in our case. And so we make some predictions with that model, and this is the values we get. But in reality, the model may look something like this. So why is there a difference between this model and reality? The problem here is that the distribution of the data is so different. In a geological context, that often comes about from bias, and it's quite a common problem that I see in a lot of different applications. So the samples here, we have our surface samples that were collected for all different types of reasons. There was no mineralization in the area, so perhaps they all have high concentrations of chemical values. There's physical access problems. They're only collected from outcropping regions. They're only collected from a geological context of interest. The data is very biased. So these differences in distributions can be quite common, where your model is no longer valid when you want to come to use it to predict. So what can you do about that? What we did in this case was to train a separate model, machine learning model, a classifier, to tell the difference between the two. And if it can tell me that this point is not part of the training set, then I should question whether or not the model is valid to apply to that point. Other things you can do is visualize the data, form some sort of density estimation in comparison between the two distributions, weight the training data more towards your query data set, or collect better data, ideally, which is what you want to do. So these are results from that problem where we're trying to predict certain chemical elements. So these are cross-validation results on the training data set we have. And the covariate shift classifier here indicates how well it was able to to tell the difference between the training data and the query data. So the higher the accuracy here, the more different those distributions are. And that's come about because we've introduced more covariates. Originally we're just using magnetics and gravity to try and predict these chemistry values, and the performance is okay, not great. When we introduced wavelets, the performance increased, the model became more specialized, so it was less valid across, became more focused on in terms of the covariate distribution. So I'll show you the results on the map there. This is that region showing the predicted log copper values and the model uncertainty, and I'm masking out areas where the model thinks that the covariates in this region are too different from the ones that we trained on, so the model's not valid in this area. When we introduce some additional covariates, a whole bunch of that area disappears. The model's not valid here, according to the classifier that we developed. You can see there that's an Ernest Henry mine with some high predicted copper values, and it does show up as being similar enough to the training data that we're confident that the model is valid in this region, and we didn't have any training points from that area. So the next example, so those last 4 examples were from the Northwest Mineral Province in Queensland. The next example is from South Australia, and this is kind of the same problem that I just spoke about in terms of predicting geochemistry spatially across the region. But here, and this is something that we're continuing to look into, is we're interested in how we could use the model in real time to inform the sampling process. So typically, GSSA, we work with GSSA to perform regolith characterisation in this area of the nullable. And typically what is done is a grid of samples across the region. So what we wanted to look into was, can we use covariates, spatial covariates, that's magnetics, there's a huge magnetic anomaly in the middle there. Gravity, I think, some DM and radiometrics and structural, geological structures there as well. Can we use those covariates to predict or to develop a model that relates these values to the soil geochemistry? And can we use that model to determine where to sample next, to either minimize the uncertainty based on our model, or to maximize the probability of finding a particular value. So in this case, we set up a mobile lab in the nullable. So at the end of every day, we took samples for the day, sorted and processed them. We had a crusher, a grinder, and a press to press the ground samples into pucks, and the PXRF machine set up to measure the geochemistry of the samples. And then the process was to develop a model based on those daily samples. And ideally, we didn't do this in this case because it was kind of a proof of concept. Ideally, use that model to inform the next day's samples. In this case, we just flew kind of a pattern back and forth across this grid. So here, not sure if you can see that, there's points just along here. They're the first day's samples, I think it's 25 samples. And the resulting model here of aluminium. In this case, we used a Gaussian process model. So this model's pretty useless because it's got such a small data set to train on. The data's from such a concentrated area within them, within the region, so not particularly useful. What you would want to do if you were running an active sampling process from the beginning is to start with a more more or less representative sample distribution across the covariate space, build a model, and then work from there. I'm showing here that up to day 5, where I think we have samples up to around here, the updated model. So to integrate, so kind of describe that process of how active sampling might work, and the reason behind it would be to try and reduce the number of samples that you ultimately take to gather information as fast as possible, and not have to do this entire grid of sampling. So to kind of demonstrate that here, after we did collect the full set of samples, I run the model with half those samples, a randomly selected half, and with all of them. And so you can see the model here is more detailed with the full set of samples, but there are features within, so using half the samples that you still get. So there's a trade-off there between how many samples you take and the level of information that you want to have, and any other constraints you want, or based on the reason for the sampling campaign in the first place. So the last example I have is a drill core characterisation example. So this one's a little bit different to all the other ones, which were geospatial prediction examples. This one we're looking at drill core imagery. So the aim of this was to try and predict lab results from spectral data. The motivation being that we use a fast, less expensive sensor that is on-site, that being the core scan spectral analyzer, to predict these values, which are costly and time-consuming to achieve through sending samples away to the lab and waiting for the results. So this is a supervised machine learning problem. So this is to give you an idea of the data pipeline for training and predicting this model. So this differs to some of the other examples, in particular Sol's example of looking at core imagery where they applied a deep learning model. Here we're applying a number of traditional machine learning models in a pipeline to achieve certain results. So we have training samples, and for every training sample we have the spectral data. We have the rock type as determined by the geologist. We have assay data from the lab and QXID mineralogy data. So given that training data from thousands of samples, we train these 4 different models. The first is a spectral feature model to reduce the spectra of the image spectra from thousands of variables down to some smaller manageable set of variables to feed into the other machine learning models. The next one is a rock classifier. So here we just use the spectral data and the rock type and train the classifier to determine the rock type based on that. The next step in the pipeline is the chemistry regressor, where we use, again, the spectral data, the rock type, and the assay results to train a model which could, given the rock type and the spectral data, output chemistry. And finally, the mineralogy estimator uses the assay and the QXID mineralogy to learn a relationship between those 2 variables, and again to output the mineralogy. Then given new data, which is just spectral data, we feed it through this pipeline to create the features, predict the rock type, predict the chemistry, and then the mineralogy. So this is some results from that project, looking at a single hole, down hole. On the left there we have the rock type. The predicted, so the actual values are all shown in black. The predicted rock type is shown in red, and it's a probabilistic prediction, so it's shaded according to the certainty the model has of that prediction. And then we're showing a number of different elements. Iron and magnesium, I'm told, are highly visible in spectral data. so relatively easy to predict. Uranium and copper, on the other hand, are not typically visible, so a spectral geologist can't look at a spectra and tell you how much copper is in there, because it doesn't correspond to any of the peaks in the spectral data. The machine learning model, while it doesn't do as well as it does for these more spectrally active elements, in particular for high values it underperforms, still is able to produce some reasonable prediction of those two elements because of their relationship to all the other elements in the data set that we have. So this is a good example of where a data-driven model can perform better than a knowledge-driven model, for example, where these variables would not be predictable from that data from a more analytical approach. Showing here the mineralogy prediction. In red is the existing model used, so that's again an analytic approach based on the chemistry, chemical equations and weights of, and a process of elimination for matching the assay data to the minerals that are formed, and the blue is the machine learning model. So mostly sort of comparable. You can see some instances where the analytic model doesn't pick, for example, that there's two modes of a particular mineral. Here also, where the machine learning model arguably doesn't do a whole lot better. So here I'm showing a YY graph, so the predicted result on the y-axis and the actual value on the x-axis. And because it's a probabilistic model here, I'm showing the upper and lower bounds of the same data of the predicted. So the green is the upper bound, the blue is the lower bound, and the red the predicted value. Again, for each of the minerals in the YY graph. So not only do you get a prediction, you also get some sense of how to value that output, whether you should be confident in it or whether you should send the sample off to the lab and have it tested instead. So to summarize, we've applied machine learning across a broad sort of set of examples across different geoscience problems, and some of the benefits basically of such approaches that you can leverage large data sets, you can make predictions and quantify model uncertainties. You can identify patterns in data that geologists may already suspect. You can provide insight to complement the traditional techniques, so to speed up certain processes or audit certain processes, potentially automate repetitive tasks and aid decision making. But there's, as has been mentioned in a number of the other talks, the model you produce is only as good as the data that you provided. And data bias is a very big problem, particularly I think in geoscience data. It's very across a lot of other domains where machine learning is provided, is applied. It's very easy to collect more data across. If you're missing data of the Siamese cat for your cat classifier, it's easy to go out and collect pictures. If you're missing certain types of data within a particular geological domain or with particular geological signatures, it's very hard or costly to go out and collect that data. So we need to be aware of the data bias when we're building the model. And that's where domain expertise comes in, especially to be able to identify upfront problems that you're going to have in applying or interpreting a model. If not, that's it.